Thank you very much, Jimmy. Thank you for this opportunity to talk here. So I'm going to talk to you about how Renault leverage machine learning to scale electric vehicle sales. So it's kind of a catchy title, but actually, as you're going to see, this is not so much about machine learning, but also about making things work all together to answer a business issue, business problem. But first, let me introduce myself in a couple of minutes. So my name is Vincent. I'm French, or Vincent. I have a PhD in physics that I defended in 2014. So here is a cute picture of the kind of things that I used to do back then. It was positron emission tomography for those who are wondering. Just a quick shout out to my university because it's not well known worldwide, but actually, according to the Shanghai ranking, which is most what it was, it's number 12 worldwide, and it's really good at mathematics and physics. So yeah, just quick shout out about that. So what did I do in the last decade? So I deployed machine learning models for large company, among other things. So at Renault, obviously, also for Chanel. I've been working there now for 2 years, working on beauty tech stuff. I worked too in L'Oréal, beauty tech stuff, for a short amount of time, and I also worked for 2 years at General Electric in the healthcare division, doing some medical imaging stuff. I also worked in several startups here in France and scale-ups. So one of them, for example, was Cruise. So we were doing based on video interviews. So you are trying to answer some some interview questions for a job. We would do automatically a ranking of candidates based on deep learning. So we made a publication based on that in AAA actually. I also worked at Jelly Smack. You may have heard of it. It's a company that was backed by SoftBank. It raised in the billion-dollar value. And I was working on forecasting the revenue of YouTube videos in order to buy them and make profit out of it. Also, among other things, I did some lectures, some teaching, so in some engineering school and business school. So at Edec Business School, one of the top business school in France, I did some teaching of classical ML. At MinParisTech, which is one of the top engineering school here, I did some teaching of deep learning. I also conducted a lot of trainings in many companies, mostly French companies, if you may have heard or not of them. So French leading banks, energy provider, and so on. Finally, one more thing about me. So I like to write, even if I don't write as much as I would like to, because I like time. So I write a bunch of articles on Medium. You can go check, have a look. It's mostly about computer vision, but not only. And last but not least, I'm the author of the Regularization Cookbook. So it's a book published by Packet. So it's really about regularization in machine learning, but not only, it's really a good, let's say, entry-level book about machine learning. It goes from linear models, linear regression, the heuristic regression, also the decision tree, like boosting, bagging. It covers also basics of deep learning up to more advanced techniques like for NLP, computer vision, convolutional networks, RNN, and so on. One interesting point about this, since it is a cookbook format, you have working codes available on GitHub for all of those examples that I provide in the book. So I guess it's really a good entry level for anyone willing to learn a bit more hands-on and practice a bit about that. So thank you for this small introduction. So now back to the topic of today. So first things first, why did Renault need to automate in the first place? So a bit of context here. It was a project that happened to me in 2019. So when Renault got in touch with me about that. So what it was back then does anytime you would like to buy an electric vehicle, well, you may actually need a charging station, of course, unless you already have it. This charging station would have to be connected to the power grid, obviously, and the cost to connect this to the power grid would be depending on many factors, but mostly the electrical path. So basically, anytime you wanted to buy an electric vehicle from Renault back then, they would send someone in your place and they would have a look and say, all right, I'm going to look around. I think the most efficient electrical path would go here and there. I'm going to measure it with a scale. and say, okay, it's 2 meters of this, 2 meters of that, and it's going to cost so much. So obviously, if you want to sell, let's say, hundreds of thousands of cars every year around the world, you are not going to send a trained specialist into everyone's house. So it was not possible to keep it that way, so they needed to automate that. So the idea that they had, well, was nothing really fancy. We could come up with that, but it's a web app. So how does it work? It's really like that. It's a UI. So basically, you are going to type in your address in this kind of search bar. It's going to pop up a satellite view, like the Google Maps one, all right? And you're going to have to give two information. So the first one is going to be, where is your house? What is your house on this map? All right. So this is the home marker. And of course, the second one that you are going to have to give is, where do you want your charging station to be located? Okay, so it can be inside the house, for example, if you have a garage, or it can be outside the house, in your garden, or in front of your house, or whatever. And then it would, within less than 1 second, or really almost in an instant, give you an estimate of how much it's gonna cost, instead of having someone send where you live and so on. So that was the idea. So you guessed it, I was in charge of making all the algorithm part. So how did I get to that? So let's take a step back. So what are the inputs and what are the parameters that we have? So the inputs are just two things, actually. So it's the location of the house, the GPS coordinates, and the location of the charging station, again, GPS coordinates. We also have some parameters to this algorithm, which are given by the business, actually. This is the linear cost of each type of surface. As I told you, depending on if you want to put a cable into a building or if you want to dig underground under concrete, it's not going to be the same cost. So it's depending on that. So I have that from the business. And so based on that, what I proposed was a two-step algorithm. So the first step is actually to make semantic segmentation from the satellite view to have for each pixel the type of surface. And the second step would be based on that, trying to compute a shortest path to to connect actually to the power grid, this charging station, and then compute the cost of that. Of course, deployment is going to be in the cloud. I'm going to talk about that. So here we have our plan. So I'm going to talk about all those steps. So first, I'm going to talk about what I did for the semantic segmentation. Then I'm going to talk about how I did the cost estimation with shortest path, but not only. I'm going to talk briefly about deployment, and if I have time, I'm going to talk about improvements and future developments for that project. All right. So first step was semantic segmentation. So most of you probably already know what is semantic segmentation. In case you don't know what it is, so it's basically classifying each pixel in a given image and giving it a class. So here we had an image. Yeah, I don't have the original image, but here we have each pixel in red being a dog, each pixel in blue being a sheep, and so on and so forth. And anything that is not a sheep or a dog here would be a background. But anyway, it's quite different from instance segmentation where you want to have separately each object. Here, I don't care about that. I mean, I don't care about knowing that a road is different from another road, or a garden is not the same as other garden. It doesn't even make sense. So I used semantic segmentation. So it works. You probably already know that, but it works like most ML problems. So basically, you have data, which are the image. I mean, you have features, which are the images, the pixels images, and you have labels, which are the mask for each of the classes. And then you train and evaluate model on top of that. Of course, also, just like most ML problems, it's not always working the way we expect it to work. So we have to add some post-processing and workarounds. We're going to talk about that right after. So first things first, the data. So I had about 3,000 images from various cities. with several light conditions, like some of them were in summer or spring, some of them more in winter or fall, so that the light is quite different. I also had different zoom levels, yeah, in different cities with different kind of well, of background and everything. It was labeled with the three following classes. So building, so here you have an image, here you have the labels. So building here is in blue, you have hard ground in red, and you have soft ground in green. So as you can see, the labels were far from perfect. Here, for example, you have a tree. Of course, below that tree, there is concrete. You can even barely see it, but yet the label were not perfect. It was considering it a soft surface, but yeah, whatever. I had to deal with that. About the model training part. So what I did was I used a UNet with a pre-trained VG16 backbone. So keep in mind that it was in 2019. I wouldn't do exactly the same today, but yeah, it was the state of the art was what it was then. Even if it was already quite old, VG16 was kind of a standard. So out of the 5 blocks of convolutional plus pooling layers, 4 of them were were frozen. The weights were frozen, meaning actually I wouldn't update the weights with backpropagation. Only the last one were not frozen, and then I would have UNet architecture on top of that. So meaning for each of the block, I would just concatenate the output with another up convolution output, and then would train all the way up and have a segmentation map. Yeah, okay, good. All right, about the image augmentation. So I did some typical image augmentation. So horizontal, vertical flips, I could do both. Some brightness and contrast randomization. Keep in mind that it was in 2019, so we didn't have albumentations back then, or it was really barely known. So you had to code that all by yourself. It was another time. About the tested losses, so I tested a few ones, so cross entropy, dice, focal. Depending on the kind of data that you have, for example, if you have imbalanced class, underrepresented class, it may help to have a different kind of loss. Actually, I think if I remember well from my notes, because it was 5 years ago, cross entropy was what worked best. I think it's mostly because all the classes were kind of balanced, but I'm not sure. For the evaluation metrics, so I used IOU, accuracy, and dice just to have an overview. And so, again, this is not from 5 years ago. I'm not 100% sure about what I'm saying here, but what I could find is that mean IOU that I had for the best models were 0.72, mean dice 0.88, NT1, sorry, and mean accuracy of 0.89. So if you know about semantic segmentation, I mean, as far as I know, it's acceptable results. I mean, it's far from perfect, but it's quite okay. Before going to showing you some results about what it did, how it performed, I'm going to make a jump into the history. And so actually, when I got later into the project, when I showed the first version to the business and they could test it out on some examples, we realized that we didn't have only to have 3 classes, but 5, because they realized that, I mean, they already knew it, but they didn't specify it, that actually you can't have an electrical path crossing a public road or a water course, because yeah, they cannot dig into a public road, they don't have authorization, and they cannot go under a water course easily. So actually, I needed to know if there was public road and water. The problem was that at that point of the project, we didn't have much time anymore. We didn't have much budget to label more data. And I was really concerned back then that even though if we had a lot of time, public road would be really complicated for the model to discriminate from just concrete, because from satellite point of view, it might be kind of the same. So what I did is a quick fix, let's say a workaround. because I didn't have so much time. So what I did is that I used Google Maps style features. So basically, if you look at Google Maps, not in satellite view, but in regular view, you have this kind of view here. And you can see that water is usually in blue. Buildings can be in a blue, sorry, yellow, gray, or blue, or whatever, red sometimes. And the roads also have specific colors. So what I did is that I used that to build a heuristic, hard-coded heuristic on top of my semantic segmentation to really have a segmentation of the public roads and the water and add it on top of my segmentation. So in the end, the result of the semantic segmentation was this kind of results. So on the left, you have the images. In the middle, you have the result of the segmentation plus, semantic segmentation plus the heuristics about roads and water. And on the right, just a blending to see that it's blending well. So here you have, the concrete in red, soft in green, sorry. In dark blue, you have buildings. In light blue, you have water, and public roads are in yellow. So it works pretty much okay. So that was the first step. Then once I had that, the second step was actually make the cost estimation out of that. So I'm going to explain to you, but it's not, I didn't have to make just a shortest path estimation. I had a few requirements on top of that. So the first one was the following. We actually needed, it was a requirement from the business that we actually needed to connect our charging station to the center of the house. I don't know if it makes much sense, but I think the rationale behind it is that we don't know for sure where we are going to connect to the power grid. So considering it's the middle of the house is an average value, and so it's going to work on average over a lot of cases. I guess that was the rationale, but I'm not sure. So the thing is, I had to find the house center. So what I had again is those 2 points, so the charging station in blue and the house, just house marker in yellow, and this image. So now I have my semantic segmentation. And so I can find all the contours with image processing of all those buildings, all right? So I have this kind of result. Next step, I'm just going to find to which contour belongs the input house point. Okay, easy with OpenCV again. You can just, I think it's point or polygon test or whatever, it's the function. And then finally, with that contour, I would just compute the center with moments, and then I would have my house center. All right. That was the first requirement. The other one for computing the shortest path was that actually the path must follow buildings' ages as much as possible. I think the rationale behind that is that if you're going to put a cable into a house, it's most likely that this cable is going to run into the walls, sorry. So we had to follow the walls as much as possible. All right, so how did I do that? So I computed, assuming you have here a bunch of pixels of a building and here a bunch of pixels of soft surface. I did a dilation, so a morphomathematical operation on my soft with OpenCV, and so that I have this new soft. All right, and what I did is just a logical AND of building and this dilated soft, so that I would give me the edges of the building. Again, I did that way because one of the requirements was to follow the edges of the building from the inside of the building, for what it's worth. So I did it that way, so I have my edges. And so in the end, on a typical example, it gives me all those pixels that are edges. All right, so now I can finally go to the shortest path computation. So for that, actually, I use Dijkstra's algorithm, which is quite famous in computer science. You may already have heard of it. So it's a shortest path computation of graph algorithm. So what I did is that I considered my image as a graph. So all the pixels are considered as vertices, all right, just like here. and I'm going to consider the edges as for all the 8 neighbors closest, all 8 closest neighbors of my pixel. So basically here you have this pixel here, and for all of its 8 neighbors, I'm going to say, all right, if this is water, then the weight is going to be really, really large, basically infinity, because I don't want to have a path going on water. If it's soft, it's going to be quite small, because soft is not so expensive. If it's edge of a building, sorry, since we want to follow the edges of the building, it's going to be really slow, so really low, sorry, the weight, and so on and so forth. And I will also adjust for diagonal with square root of 2, of course. And based on that, I could apply Dijkstra's algorithm and find the shortest path from one point to another. So from my house center to the charging station. So here is an example. So I had this image. So in this one, on blue, this is the house location. So here I didn't display it, but this is the computed center of the house. This is a L shape, so this is kind of here. And in kind of yellow, this is a charging station location. And so here is the path. So as you can see, it's kind of following the edge of the building. So it's not perfect. There is some aliasing, but well, we don't care so much for this kind of operation. And so here is the result. So based on that, I can finally compute my cost estimation. So I have to find, for that, I need 2 more information actually. One is a parameter given by the business. So it's the linear cost for each of the surface type. So for example, just giving a number, it's different for each country, but for concrete, for example, it's going to be 200 euros per meter to dig in. So this is one thing that I need. And the other thing that I need is the actual length of 1 pixel, because I have to know, well, how much is it 1 pixel to compute the actual length of the path. So to do that, it's actually depending on 2 things, the latitude and the zoom level. You have to derive that, you have to know the Mercator projection, which is used by Google Maps. So for sure, my background in physics could help a bit about that. So here is a formula if you're interested into that. And so the length for this given example here was, the computed length at least, was 11.5 meters. So here we are, and then we could just apply a factor for each computed length depending on the type of surface and have an estimate of the cost. All right, so now we have our cost estimation for a given input. Next step is deployment. So I'm not going to dig in so much into that, but just give you a few information. So it was served as a Flask API. It was deployed on AWS with load balancer and autoscaler. To be honest, we didn't put so much effort into that part. We didn't have a really complicated infrastructure. Why? Just because we didn't have the need to, we had quite a small traffic. This web app was not openly exposed for everyone. It was only for buyers after a given point into the process. So we didn't have millions of queries per day. It was more like hundreds to thousands, but definitely not so much. Just as an example, here is the input payload. So you have the GPS location of the charger and the GPS location of the house, electric location. Well, it's arguable, the name, but anyway. Here is the output that I would return to the backend. So you have the path length overall. You would have the decomposition for all types of surface, so concrete, building, soft, the length unit, of course, and some more information that were informative to raise warnings or have more information for the business, such as is the charger inside the house or is it outside? Is it in a different building? Because some people had a garage that was separated from the building, so it would raise some warning. Also, where was the charger and so on. So this kind of output. All right. And also one more thing that we had to do after a couple of months of deployment. I mean, it had to happen, but we had to add some tests because actually at some point I told you I used some heuristics to compute where are the roads and the water. But as you can see, during 2023, I guess Google Maps changed its color palette. So as you can see, it was before, so most of the main roads were yellow, for example. Now they are kind of green bluish. So it broke, of course, all the pipeline because it was the hard-coded heuristics were not working anymore. So we added a few tests. I mean, we fixed that, of course, but we added a few tests to check some data drift that are running daily. So every day we are running some tests that check if the values are really what are expected against some references, and we give those outputs into a channel, Slack channel, so that everyone can know the status inside the team on a daily basis quite easily. And we also added some model or algo drift, I would say, with some past estimation to make sure everything works smoothly at this level too. I have a raised hand. I don't know, Jimmy, if I'm going to take that at the end or I don't know how it works.
Yeah, if you raise your hand, the best bet is to ask your question in the Q&A box. We don't turn on audio for other folks as it can tend to be disruptive. So please ask
All
your
right.
question in the Q&A.
Thank you, Jimmy. Thank you very much. All right, so I'm just going to go ahead and take questions at the end. So I have a few more minutes. I'm going to talk about improvements and I'm going to conclude. Uh, so actually, what I presented to you is not working. I mean, it is working, but in that first version, it was taking up to 30 seconds to just compute a single query, which was not acceptable from a customer point of view, of course. Actually, all the computing time was really from different algorithm. It was taking most of the computing resources. The model inference were about 200 milliseconds. All the image processing were really quite fast, but different algorithm was taking a lot of time. So I did two improvements to make it fit into a 1 second query or less most of the time, actually, or every time. So the first one is quite obvious. It's just image binning. So to have an accurate enough semantic segmentation, I was using 512 pixel size images from the satellite. So as far as, I mean, this is good for this part, but when I'm going into the difference algorithm now, what I do is that I'm making a 2x2 binning of the images. So I have now 256 per 256 images. So it gets down, it divides the processing time by a factor of 4. And the other improvements that I did is adaptive cropping. So just let me give you a word about that. So the thing is that most of the time, once you have your main information, which is a charging station first, and then the house on trade, which are those 2 points in this example, most of the image becomes useless because most of the time you won't have a path that will go very far from those 2 points. It's going to go around this place. So what I did is that I kept the min and max position of those 2 points, added a margin of, let's say, 10 pixels around them, and cropped everything else. And so I kept only basically everything that is not grayed out to feed into the distress algorithm. So most of the time I would have, let's say, less than 10% of the image into distress algorithm, making it much, much faster. And so it happens sometimes that I have points that are really too far apart. Like, for example, if I have those two yellow and red points really on opposite corners, in which case I would have a threshold and just make unzoom. So I would unzoom from one step from the Google image and then redo it all again. It would save me a lot of time. And so, yeah, it would allow me to, every time I have a query, to make it run in less than 1 second. And so make it acceptable for the business and the customer. So I'm not going to go into future developments. Just to conclude, I mean, just a recap of what I just told you. So the need to automate was really answered with a web app, and I did the following algorithm. So it was first step semantic segmentation with 3 + 2 classes, actually. Three originally, and then 2 classes with heuristics and the Google Maps. Then the cost estimation with house center, buildings edges, shortest path with Dijkstra's algorithm, and cost estimation using the market loss projection. Finally, it was deployed into the cloud with Flask API, and I had to do some processing optimization. So just as I told you, image binning and adaptive cropping. And that's it for me. Any question? I see there is one. Jimmy, if you want to step in and add
Yeah, for
anything.
sure. For sure. There are two questions. There's one in the chat and the one in the Q&A. We'll start with the one in the chat. And this was in relation to your slide around 5 improvements. So it was near the end. For data drifting, what did you use?
Yeah, okay, that's a good question. This is nothing fancy that I used actually. I just have some references. So what I do is that when I'm doing data drift computation, I'm just going to have this kind of images, and I'm gonna say, okay, I expect on this image to have at this specific location a public road, and I want it to be in that color. So I have a few hard-coded, I would say, references, and I'm going to test that against the current API output of Google Maps. And so it's going to let me check that everything is working fine. And if I have any discrepancy, then there is a warning, it's not working anymore. There might be some data drift. Hope that answers your question.
And we have another question that came in towards the end. Are you using imagery from Maxar, Sentinel, Airbus, or any other sources?
To be honest, no, I don't know any of those. I'm not an expert in satellite imagery. So no, I mean, it was a data set. I cannot say much about it because it was a bit, maybe it was 4 years ago, or even 5 now. I don't remember where they got it. I think it was really Google Images from satellite view like that, that we selected. And then they got it labeled, but I'm not 100% sure.
Okay, and one final question from the Q&A. Can you please talk a little bit more about image binding? Binning? Is it
Oh yeah,
image
yeah,
acquisition?
sure. I mean, it's just a fancy name, image binning, but it's just a rescaling basically. So it's just like you are taking your image, which is 512 pixels per 405 pixels, and then you are going to make, for example, CV2.resize to 256. So the only thing that you have to take care in this case, because I'm doing that on images that look actually, sorry. This is actually semantic segmentation output, so you have to make sure that you keep some consistency on the cases. You don't want to mess that up, so you have to add some post-processing to this. But yeah, basically it's just a resize plus some heuristics to make it consistent, I would say, overall.